Welcome back to the deep dive. Today we are doing something that feels, I don't know, a little bit illegal.
Illegal, yeah.
Not in the judicial sense, but in the laws of physics sense. Usually we take a stack of articles about history or tech or, supply chains, and we try to make sense of the world around us.
Right. The here and now.
But today we are leaving the world behind entirely.
We are leaving the solar system. We are leaving the galaxy. We are going to a place where the map doesn't just stop. The map shreds itself.
We are talking about black holes, but, and this is, I think, the key distinction for today's deep dives, we aren't doing the pop science overview where we just say they are heavy and invisible.
No, not at all.
We have a stack of sources here that gets into the nitty-gritty of the physics. We're talking general relativity, quantum field theory, tidal mechanics.
We are going to simulate a journey.
Exactly. We're going to simulate what happens to you, the listener, if you were to pilot a spacecraft directly into a black hole. We're going to narrate this strictly according to the laws of physics.
No magic wormholes.
No bookshelves in the fifth dimension. Just gravity, radiation, and the bending of space-time itself.
It is a one-way trip. And frankly, looking at these notes, it's a terrifying one.
It really is.
But it's also beautiful in a very stark mathematical way.
So let's set the stage. You are the traveler. You are strapped into the pilot seat of let's say, a reinforced, shielded spacecraft. I'm going to be your voice of curiosity. And our expert here is going to be, well, let's call you mission control.
Okay.
You're the one telling us why the dashboard is screaming at us.
I'll do my best to keep us alive as long as possible. But remember, the destination here it's the breaking point of reality itself.
Right. So part one, the approach. We are cruising through space. The stars are static points of light. But ahead of us, there is something that shouldn't be there.
Or rather, a lack of something.
A hole in the stars.
We really need to define the object first, because the biggest misconception people have, and I see this in the listener questions all the time, is that a black hole is a hole, like a drain in a bathtub.
Right. Like someone pulled the plug on the universe and everything is just swirling down.
But that implies it's empty.
Yeah.
Or that it's like a two-dimensional dip in the fabric of space. It's not. A black hole is an object. It is a sphere. It is a concentration of mass.
Okay, let's unpack that. Concentration of mass.
Think about the source material we have on gravity. The fundamental rule is every object with mass attracts others. You have mass, the Earth has mass, so you attract each other. It keeps you in your chair.
Just full enough.
Now, usually objects have a lot of empty space in them. Atoms are mostly empty space.
Mm-hmm.
But a black hole,
it's the ultimate trash compactor.
it's mass without the volume. I mean, imagine taking the entire Earth, all the mountains, the oceans, the iron core, everything, and crushing it down. Not to the size of a marble, not even close. You crush it down to the size of a peanut.
Wow.
It still has the exact same mass. It still has the same gravity pulling on things far away.
Yeah.
But the density is, well, the math says it's infinite.
So as we approach this thing in our ship, we aren't seeing a hole. We are seeing a sphere of absolute darkness. It cuts a perfect black circle out of the star field.
And because of the gravity, it's not just blocking the stars behind it. It's bending the light around it.
So you see warped stars?
You see the stars that are actually behind the black hole, but their light has been bent around the edge, so they look like they're smeared out into a ring, a halo of light around the darkness.
Einstein rings. I've seen the picture.
Exactly. It looks like a lens, a dark lens suspended in the void. But here is the thing. Unless this black hole has been sitting in a perfect vacuum for billions and billions of years, it's rarely just a quiet black sphere.
Because things fall into it. It's a messy eater.
Right. And this is the accretion environment. This is where our ship's sensors start going absolutely haywire.
Okay.
You see, when gas and dust and, ripped up stars fall toward a black hole, they don't fall straight in. They spiral, like water circling a drain, but at speeds that are just hard to comprehend.
And our outline mentions energy transfer. It says, impacts convert kinetic energy into heat. Energy increases with velocity squared.
And that velocity squared part is the real killer there.
What do you mean?
If you crash two cars at 60 miles an hour, it's a mess. But if you crash two gas clouds at, say, 20% of the speed of light, you don't just get a bang. You get nuclear fusion temperatures. You get plasma hotter than the core of the sun.
So this dark sphere is surrounded by a glowing, swirling disk of superheated matter.
A disk that is brighter than 1,000 suns. It's glowing this brilliant blue-white. And it's not just visible light. The source notes really emphasize high-energy radiation.
The bad stuff.
Yeah.
X-rays, gamma rays.
This is an environment that is actively, aggressively hostile to biology. I mean, if you roll down the window, which please don't,
I will.
you wouldn't just get a sunburn. The radiation is so intense it would literally ionize the atoms in your body.
Yeah.
It would strip the electrons right off your DNA.
So our shields are up. They have to be. We're pushing through this blinding storm of plasma. The ship is vibrating. The heat is rising. And we're caught in the grip of its gravity.
This is where we have to talk about orbital mechanics, because it's not like orbiting the Earth.
Usually orbit is a safe place, right? The International Space Station orbits Earth. The moon orbits Earth. It's a stable balance.
It is a balance between your velocity, how fast you're moving sideways, and the gravity pulling you down. You're constantly falling, but you keep missing.
A great way to put it.
But as we get closer and closer to the black hole, that balance gets precarious.
Right.
To stay in orbit, to keep from falling in, you have to move faster.
And faster.
And faster.
And faster.
Until you hit the limit, there comes a point, a line called the innermost stable orbit, where to maintain that balance, you would have to move at the speed of light.
But you can't.
Since matter can't move at the speed of light, stable orbits become impossible inside that line.
So there's no parking here.
Yeah.
You either fly past at an incredible speed or you go in.
And we, strictly for the sake of science, are going in.
We're committed now.
We are steering the ship toward the darkness. We're past the brightest part of the accretion disk now. The noise of the radiation static is fading. It's getting quieter, darker.
And we are approaching the line, the famous line, the event horizon.
The Schwarzschild radius.
Yeah.
The point of no return.
This brings us to part 2 of our journey, crossing the horizon. And this is where the research gets really, really mind-bending because it forces us to split reality in two.
It does. It absolutely does. We have to separate what you, the traveler, experience from what a distant observer sees.
Okay, let's play this out. I'm in the ship. I'm the traveler. You are back on Earth, looking at me through some kind of super powerful telescope.
Safely sipping my coffee, billions of miles away, watching you fall.
So what do you see? What happens to me from your perspective?
Well, I'm watching a strobe light on your ship. Let's say it flashes once every second. Tick, tick, tick. Nice and regular.
Okay.
As you get closer to the black hole, the gravity is pulling on everything, including light, including time.
This is time dilation.
This is the core of it. According to the source, strong gravity slows time relative to distant observers. So through my telescope, I see your clock slowing down. The ticks get further and further apart.
Thick talk.
Exactly. 1 second between flashes becomes 2 seconds, then 10, then a whole minute.
So I'm moving in slow motion.
To me, yes.
Yeah.
And impossibly slow motion.
Okay.
If you waved your hand, it might take a year for you to finish the wave. And at the exact same time, the light coming from your ship is struggling to climb out of that immense gravity well. It's losing energy.
Which changes its color. This is a gravitational redshift.
Right. High energy light is blue, low energy light is red. So as your light loses energy, I see your ship turning from its normal color to red, then a deep infrared. Then it becomes just radio waves. You are literally fading out.
Eventually, what's the last thing you see?
Eventually you freeze. The source says it very clearly. To distant observers, objects appear frozen at the horizon. I never, ever actually see you cross the line. Never. To the entire outside universe, you just become a faint, red, frozen ghost plastered against the darkness for all eternity.
That is profound. History effectively ends for me, from your perspective. My story is over.
From my perspective, yes. But, and here's the incredible twist, that is not your reality.
Let's switch cameras. I'm inside the cockpit. I look at my watch.
Your watch is ticking normally, 1 second per second. You check your pulse. It's probably racing from fear, but it's rhythmic. You look out the window. You don't feel slow at all.
The source says, locally, they continue normally.
That's Einstein's equivalence principle in action. The feeling of free fall is indistinguishable from the feeling of floating in zero gravity. You just drift. You drift toward the horizon. You cross the line. And absolutely nothing happens.
No sirens, no flashing lights, no warning. Reality ending sign on my dashboard.
No physical barrier. It's just a mathematical line in space. One moment you are outside, where you could, in theory, escape. The next moment you are inside where you can't. And you wouldn't even notice the transition.
But something has changed, fundamentally, even if I can't feel it.
Everything has changed. You have crossed the causality limit.
Okay, let's unpack that because it sounds very philosophical.
It's purely geometrical, actually. The definition of the event horizon is the point where the escape velocity exceeds the speed of light.
Right. Faster than light travel is impossible.
And since nothing in the universe can travel faster than light, nothing can get out. No information, No matter, no light, nothing.
So I can't turn the ship around.
Even if you had infinite fuel, even if you had an engine that could push you at 99.999% of light speed, it wouldn't matter. Space itself is falling inward toward the center faster than you can move outward.
I am on a waterfall that is moving faster than I can possibly swim.
Precisely. And this leads to a terrifying realization for you in that cockpit. The direction away from the black hole, it no longer exists as a direction in space.
What do you mean? How can a direction not exist?
I mean that inside the horizon, space and time effectively swap roles. This is very, very hard to visualize. But think about time in your normal life. Can you move backward in time?
No. I can only move forward toward tomorrow. It's a one-way street.
Exactly. It's inevitable.
Mm-hmm.
Inside a black hole, the singularity, the center, becomes a point in your future. It's your personal tomorrow. It is no longer a place in front of you. It is a moment in time that is waiting for you.
So I can no more avoid hitting the center than I can avoid next Tuesday.
That's the perfect analogy. You can wiggle around in space, you can go left, right, up, down,
Yeah.
but all paths, every single possible trajectory, ends at the singularity.
That is deeply claustrophobic. The entire universe has become a one-way street and there's a brick wall at the end of it.
And you are rushing down it. Which brings us to part 3. Inside the black hole, you've crossed the line. You are, for the moment, alive, but things are about to get very, very uncomfortable.
The notes mention tidal forces and a word I absolutely love, spaghettification.
It sounds funny, doesn't it? Like a term from a cartoon?
It does.
It is actually a horrific clinical description of biological and physical destruction.
So why does gravity stretch me? I thought gravity just pulls things down, uniformly.
It does. But the strength of gravity depends on distance. The closer you are to the massive object, the stronger the pull.
The inverse square law.
Right. Now, imagine you are falling feet first toward the center, the singularity. Your feet are, let's say, 6 feet closer to the singularity than your head is.
6 feet isn't much in the grand scheme of things.
In deep space, no.
Yeah.
But inside a black hole, the gravitational gradient, the way the gravity ramps up, is so incredibly steep that the difference in pull over just 6 feet is massive. Your feet are being pulled downward with thousands of G's more force than your head is.
So my body's being put on a medieval rack.
A rack that pulls with a force that approaches infinity. You feel your joints popping, your spine elongating, your muscles harrowing. You are being stretched into a long, thin noodle of atoms.
Hence spaghettification.
And it's not just stretching. There's a squeezing component, too. Remember, everything is filing toward a single point, the center. So if you hold out your arms to your sides, your left hand wants to go to the center, and your right hand wants to go to the center. They're being pulled together.
So I'm being stretched vertically and crushed horizontally at the same time.
You are being extruded, like toothpaste from a tube.
That's a vivid image. And this happens to the ship, too.
The ship groans, the hull buckles, the rivets pop. Eventually, these tidal forces overcome the electromagnetic bonds that hold matter together. The ship snaps. Then you snap. Then your very molecules snap.
Now, wait. We have to make a distinction here based on the research. This experience, this spaghettification, it happens at different times depending on the size of the black hole.
Oh, that is a crucial point.
Okay.
Absolutely.
Yeah.
If you fall into a small black hole, a stellar mass hole, maybe a few times the mass of our sun, this stretching happens before you even cross the horizon.
So you're dead before you even get inside.
You are spaghetti before you ever cross that line of no return. The journey ends before it really begins.
But if it's a supermassive black hole, like Sagittarius A, the one at the center of our galaxy.
This horizon is much, much further out from the center, where the gravitational gradient is gentler. You could actually cross the event horizon of a supermassive black hole and survive for hours, maybe even days, depending on the mass, before the tidal forces become lethal.
So let's assume we picked a big one. We're smart travelers. We are still alive inside. We aren't spaghetti yet. What are we seeing?
This is what our notes call the visuals of isolation, and it is haunting.
The outline mentions light speed delay and relativistic aberration. That sounds complicated.
Aberration is just a fancy way of describing how your field of view changes when you move very, very fast. Imagine driving your car in the rain. Even if the rain is coming straight down, if you drive fast, it seems to come at you from the front, from the direction you're moving.
Right, it hits the front windshield.
Exactly. As you fall into the black hole, you are accelerating to near the speed of light. So the light from the universe behind you, all the stars, the galaxy, that safe place you came from, gets compressed. It shrinks into a smaller and smaller circle of light behind your head.
So the sky becomes a tunnel. The view out my back window gets smaller and
A
smaller.
tunnel that is closing.
Yeah.
And because of the Doppler effect, the same thing that makes an ambulance siren change pitch, that light is getting energized. It's blue shifted. The light from those distant stars turns blue, then violet. Then it's shifted into hard X-rays and gamma rays. You essentially have a blinding spotlight of the entire universe's history beaming down on the back of your head.
And in front of me, toward the center.
Darkness. Absolute perfect darkness. Because no light can come from the singularity to your eyes. You are falling into a void, chased by the ghost of the world you left behind.
And the vacuum itself, the environment.
It's cold. The source mentions vacuum exposure. Heat transfer occurs mainly through radiation. Even though there's that incredible radiation from behind you, the space immediately around you is empty. It's the loneliest place in existence.
Until we hit the bottom. Which brings us to part 4, the physics problem. We are rushing toward the singularity.
And this is where our guide, the known laws of physics, starts to stutter and then just goes silent.
We talked about gravity and mass, but at the very center, the math just goes to infinity.
General relativity, which has been our perfect guide so far, predicts that at the center, all that mass, millions or billions of suns worth of mass, is crushed into a point of zero volume.
Infinite density, infinite space-time curvature.
And scientists, physicists, they hate the word infinite, don't they?
They despise it.
In physics, infinity usually just means we made a mistake, or more accurately, our theory is broken here. A singularity is essentially a big flashing neon sign that says, insert new physics here. Our current rules don't apply.
And this leads to the paradox of information. This is a huge topic in the notes, a real modern physics civil war.
It's the battle of the century. In the red corner, we have general relativity, our champion of the big and heavy, which says you and your ship are crushed out of existence, annihilated.
And in the blue corner.
In the blue corner, we have quantum mechanics, our champion of the small and weird.
And quantum mechanics has one unbreakable central rule. Information cannot be destroyed.
Exactly. The universe, in a quantum sense, is deterministic. If I burn a book, strictly speaking, I could reconstruct the text if I captured every single photon, every ash particle, every molecule of smoke. The information is scrambled, but it's still there. The universe remembers.
But if I fall into a black hole...
And the black hole eventually evaporates, which is a concept from Stephen Hawking we can get into. Where did the information about you go? If you are crushed to absolute nothing at the singularity, your information is gone forever. That breaks quantum mechanics, one of the pillars of modern science.
So we have a standoff, a fundamental contradiction between our two best theories of the universe.
We do. Because of this standoff, we have some absolutely wild theories about what really happens down there. Which brings us to part 5, modern theories.
So since we can't actually go there and come back to write a TripAdvisor review, what do the theorists say is happening?
Well, one idea born directly from this information paradox is the firewall hypothesis.
The outline here talks about radiation and quantum transitions.
Right. The firewall hypothesis suggests that the smooth, safe, drama-free event horizon we talked about earlier is wrong. It's an illusion.
What's there instead?
It suggests that because of complex quantum entanglement effects, there is a literal wall of high-energy particles at the horizon, a curtain of fire.
So I don't float in peacefully, I just hit a brick wall of fire.
You are incinerated the moment you touch the edge. That solves the information paradox, because you never actually get inside to have your information destroyed. It's radiated back out immediately.
That's disappointing. I like the floating inside version of the story better.
It's certainly less dramatic. But, okay, here is a stranger one. The concept of vacuum instability.
The source material here is fascinating. It talks about something called vacuum decay.
Most people think of a vacuum as nothing, just empty space. But in physics, a vacuum is just the lowest possible energy state of a field. It's the ground floor of reality.
But the source says a lower energy vacuum state could theoretically expand. What does that mean?
It means our vacuum might not be the true ground floor. Imagine you're standing on a floor, but you don't realize it's actually a trap door. And below it, there is a sub-basement, a state of even lower energy.
Okay.
The extreme pressure and density inside a black hole might be enough to kick the vacuum of space, our reality, down to that lower level.
So the laws of physics themselves might change inside the black hole.
Instantly and fundamentally. The source mentions a false vacuum bubble. Inside that bubble, the fundamental constants that govern our universe, The mass of an electron, the strength of magnetism, the speed of light could all flip to new values.
So I'm not just crushed, I'm transmuted. I enter a region with a different operating system for reality.
Matter as we know it might not be able to exist in that new vacuum. You might just dissolve into a soup of exotic particles that don't obey any of our rules.
And this connects to the heat death concept. How does that fit in?
In a way, the source connects the interior to heat death. Over immense timescales, stars burn out, leaving cold, diffuse matter. Because of the extreme time distortion near this singularity, looking into a black hole might be like looking at the final, cold, empty state of the universe. All the complexity has been erased.
Or looking at the beginning of a new one.
That's the most hopeful and maybe the most beautiful idea, the quantum gravity speculation. Some physicists propose that the singularity doesn't crush to an infinite point. It bounces. It reaches a maximum but not infinite density, something called Planck density, and then rebounds outward. But because it can't explode back into our universe because of the event horizon, it creates a new bubble of spacetime, a baby universe.
That is beautiful. Every black hole is a seed for a new cosmos.
It's possible. It would mean that our own Big Bang might have just been the other side of a black hole in some vast parent universe.
So we've traveled from the chaos of the accretion disk, through the quiet of the horizon, we've been stretched into spaghetti, and possibly birthed in a new cosmos in the process.
All in a day's work for a theoretical physicist.
Let's wrap this up with part 6, the ending perspective. Because this isn't just about cool space phenomena. This journey, it really changes how we see reality.
It has to. It forces us to confront the nature of time and reality.
The fact that, as the source says, clocks near dense objects tick measurably slower means time isn't universal. It's not a cosmic clock ticking the same for everyone.
It's not. There is no now that applies to the whole universe. Your now, inside the whole, is completely and utterly disconnected from my now outside. We are separated not just by distance, but by causality itself.
It really highlights the limits of human understanding, doesn't it?
It's the ultimate limit. We are creatures of observation. The entire scientific method is based on observe, hypothesize, test. But a black hole puts up a giant cosmic sign that says, no observation allowed.
The light speed delay and the causality limits mean there are truths in the universe that we are physically forbidden from ever knowing directly.
We can calculate the orbit, we can weigh the monster by watching stars move around it, but we can never, ever know what the belly of the beast feels like.
Unless we go there and don't come back.
Which I would strongly not recommend.
I want to leave with this final thought from the source material, the bit on vacuum decay. It says, this concept suggests our reality is fragile.
It is. We think of the ground beneath our feet and the empty space above us as stable, eternal, reliable things. But a black hole shows us that space can be twisted into a pretzel, time can be stopped in its tracks, and the vacuum itself, the very bedrock of existence, can shatter.
So, is the interior of a black hole a destruction of reality?
Or is it a transition?
A transition to a new state of vacuum energy we can't yet comprehend.
I like to think it's a door, but it's a door that locks permanently behind you.
On that note, I think we will keep our spacecraft safely in orbit around a nice, boring planet for the next trip.
Sounds like a plan. A much safer plan.
Thanks for taking the plunge with us. This has been The Deep Dive.
Stay curious.
See you next time.